Welcome back to the Fundamentals of Attosecond Science and Technology, or FAST, the course we bring from IIT Madras and IIT Tirupati. We are now entering week 6 of this course, and of course, things have warmed up quite a bit, and we would like to take things forward as per our plans. In this week, we will continue to be in this module on femtosecond laser pulses, and we are into the sixth interactive session of this course. As always, we continue to refer to the standard sources that we have so far been using, which is the book by Roulier, Femtosecond Laser Pulses, the book by Chang, that is Fundamentals of Attosecond Optics, and the Principles of Optics by Born and Wolf. And once again, thanks to Professor Trebino for his inputs and lecture materials. In today's lecture and going through this week, we will do this and more. But in particular, we will recap the last few lectures where we covered an important section of our syllabus and knowledge, which is essentially to introduce the time and frequency domain description of pulses, concepts such as instantaneous frequency, phase terms involved in the description of femtosecond pulses or optical light pulses, not just in the femtosecond domain. Many of these concepts essentially are applicable through a whole lot of um, electromagnetic wave pulses, because the formalism is the same. The underlying formalism is that of Maxwell's equations and the wave equation, and things that are derived essentially from these first principles. And particularly in this lecture and the next, we will look at these pulses, and because we are in the optical domain, femtosecond pulses, further in detail. When I say optical domain, I also take the liberty of including infrared into it. As you must be aware, we have near infrared, infrared, and far infrared to be one classification of the infrared domain, but you would have also heard NWIR, SWIR, LWIR, and so on. These are another way of classifying the infrared domain, but anything that is beyond the optical goes into the infrared, which merges into the microwave uh, sort of seamlessly. These terms, of course, come up because of the technology involved in either just generation of these light pulses or electromagnetic waves, or generation and detection. So we will have a bias in that sense towards optical light pulses and infrared light pulses, which essentially come out of laser sources, all of which operate on very similar principles. So the phase terms and the interpretation, we already got a peek into group delay and group delay dispersion. We will continue with that and then look into what we have been already at some level we have had a feel for, that is higher order terms in the time domain description of the uh, phase factor, which leads to positive or negative chirps, their characteristics, and so on. So let's jump in. Okay, first and foremost, when we recap these pulses, which again I once again use the same iconic picture where the light pulse is shown, the electric field and time scales are not even labeled in particular numbers. This applies in a fairly unified way across an entire spectral region, or perhaps even more. So a typical pulse has this form. You have an envelope and you have a carrier, or I should have actually said you have a carrier wave with an envelope that is modulating the carrier wave on top of it. Inside or beneath the envelope, the carrier essentially can have, or carrier essentially has fast oscillations whose frequency need not be constant across the time, that is where the envelope has appreciable non-zero amplitude. These oscillations can essentially have a varying period of oscillation or time period or frequency. This led us to the concept of an instantaneous frequency. The instantaneous frequency, which is 1 over the, you can say, local or instantaneous period, in this case increases going from left to right in the increasing direction of time. One should also note that though time usually is a coordinate which essentially conventionally takes positive values, that is to say, going from a well-defined zero or even a past towards the future, it's an increasing coordinate and things move along in the so-called forward direction of time. In the case of light pulses, we have the habit of using a local reference in a frame of reference in which the pulse itself remains stationary, that is a co-moving frame that moves with an appropriate velocity along with the pulse, in which case we define the zero of time to match the maximum of the envelope, which you can see here, and referenced with respect to that zero we have a negative and positive side of the pulse. The positive side leads the pulse, it's the leading edge, and the negative side is the lagging edge. One should stick to a conventional definition about this, considering the way in which pulses propagate and the way in which we write these equations. So don't forget the fact that this entire scenario is described by a function which has the form of x minus vt, where x is the spatial coordinate and t is the time, v is a velocity. We looked at this in the time domain, where the complete electric field describing the pulse, which is a real function of time at a given point in space, is described by the envelope of the pulse, which is the square root of I of t, where I is what we call the intensity function. And we have in the exponent, the complex exponent, two terms: a fast varying carrier frequency omega naught multiplying t, minus a phase term phi of t, which is essentially again a relatively slow variation of the phase along similar time scales as the envelope function, which is square root of I of t. The entire pulse being described by a real electric field, this function needs to be written as a half of this quantity plus its complex conjugate, which is essentially to say we consider the real part of this complex entity, which is an envelope multiplying e to the power I times the two phase terms. Now, furthermore, we can take out the complex, the fast varying carrier part, and define the complex amplitude E of t. Note the difference between the two E's, the one earlier which was a script T, which contained the carrier frequency term, and this amplitude term which has the square root of I of t. I is a real valued function. It is the absolute value square of some quantity, and it has a square root. So at best we have a choice between considering the positive or the negative root. We will stick to the positive root, of course, because negative is just a phase factor of pi. There is no further information contained in that choice. But once you define the envelope, which is a real quantity, we here have the rest of the phase term, which is exponent of minus I phi t, and we can see that the omega naught t term is conspicuous by absence. So that means the carrier is no more something we bother about. The carrier frequency is just a number, we bookkeep it, and for the rest we have the so-called complex amplitude. So the complex amplitude is everything except the fast variations underneath the envelope, which we have been sketching identically across a few sessions. Among these, the square root of I of t, which is the real part alone, or the real amplitude alone, is called appropriately the real amplitude, sometimes given the symbol A of t. So we may use these symbols interchangeably. So A of t is square root of I of t. If we sketch this for the case of what we may call an ideal Gaussian pulse. In the case of the ideal Gaussian pulse, phi of t, ideal meaning just a Gaussian pulse, that is to say, phi of t is identically 0 for all values of time. The values of time that we should really be bothered about or concerned about is only those where the amplitude is appreciably away from 0. Everywhere else it is essentially negligible, albeit the Gaussian function never really goes to 0 except in the asymptotic limit of infinite, the variable t in this case going to infinity, right? So that being the case, the phi of t function needs to be carefully either known or measured where the envelope is appreciable, and over there if phi of t is a constant, there is no variation, then we can just set it to 0 because only relative phase factors really become important, in which case we have a uniform frequency sweeping across the pulse. When it comes to the carrier, there is no variation in the carrier frequency, whether I consider the first cycle where my pointer is hovering or the next or the subsequent ones, going all the way through to the maximum of the envelope and coming down, right? This is an idealization, of course, and we have an envelope for the field and intensity, that is I of t, which is the red curve, and square root of I of t, which is the gray curve on top. We moved on to the frequency domain description of these pulses, where we have equivalent descriptions of the same kind of quantities: the intensity in the time domain, the phase function in the time domain, I of t and phi of t, as well as the spectrum now corresponding to the intensity in the spectral domain. So we could call this the spectral amplitude function, or the spectral, actually we should call it the spectral intensity function. And corresponding to this temporal phase, we have a spectral phase. So I of t has a counterpart in the spectral domain, which is S of omega, and phi of t from the time domain has a counterpart in the spectral domain, which is phi of omega, right? Doing so, if we consider now the Fourier transform of E of t, owing to the fact that we are prejudiced towards describing these phenomena so far in the time domain, owing to the way we developed everything, right, from Maxwell's equations to wave equation and these propagating phenomena, E of t is in the temporal domain. Fourier transform this faithfully, and in the spectral domain this yields us two terms, one from I of t exponent of this factor plus the second term, which is its complex conjugate. This Fourier transform yields us first a term which is a half of the square root of s of omega minus omega naught, so a shifted spectral amplitude or intensity term, and likewise a shifted spectral phase term phi of omega minus omega naught. The second term contains s of minus omega naught and the exponent with a phi of minus omega naught. So these are two functional forms which mirror each other on either side of the omega is equal to 0 reference point on the spectral frequency scale, right? So with that being the case, these two terms, while not complex conjugates of each other, do not really have any exclusive information in one of them which is not there in the other. In other words, the two terms contain the same information, albeit on either side of the omega is equal to 0 point, owing to which we then say, okay, we can now use a new reference. We forget about even omega naught, have an e tilde of omega and reference it to omega naught being 0, simply because we decided to bookkeep that, and this now has a simple form. If I center the pulse not at its actual central frequency but just at center the pulse spectrum at 0, and consider only the detuning of the actual frequency from the central frequency omega naught. If we do that, then E tilde of omega is per definition the square root of the spectral intensity function, or the power spectrum as it's sometimes called, S of omega, multiplied by exponent of minus I phi of omega. The same information is contained using the same variables E, S and phi, so that although we will sort of use this interchangeably, we will have in this case, in considering all these cases, an amplitude, a spectral amplitude part, a spectral phase part, a spectral amplitude part, and a spectral phase part, all of which contain the same information identically. Okay. Normally, we tend to use just this component, albeit sometimes you can find in literature the way things are written. You can also find descriptions where we essentially describe everything about a central frequency which is zero, which is sometimes what we are also going to do in this course. So I'm just trying to build your awareness about what is what, so that you can move across various definitions. So like we had in the time case, we have the spectrum or the spectral intensity. Both are synonymous. S of omega, it is the absolute value square of E tilde of omega. Spectral phase, the inverse tangent or arctang multiplied by minus 1 of the imaginary by the real parts of this field quantity. Then phi of omega likewise can be shown to be minus the imaginary part of the log of E tilde and the frequency domain. Okay. Now we considered examples like the Gaussian pulse. I will not dwell on this too much, with the flat spectral phase set to 0 across in the time domain and the frequency domains. And this was sort of an iconic illustration where we understood the meaning of the spectral phase term, where if the spectral phase were to be identically 0 across various frequencies, and we considered this example of 6 omegas, then all of them constructively interfere at time t is equal to 0. And if we now had a linear shift in the spectral phase of 0.2 across each of these omegas going from omega 1 to omega 6, we then have the maxima shifted as shown along this dotted line. Ergo, when we sum up these amplitudes, the maxima are aligned at some forward time, that is away from the 0 where the two vertical axes are shown to intersect, the vertical and the horizontal, and we essentially would have had a pulse that would have propagated forward. This illustrates the fact that a pure propagation of the pulse without suffering any deformation simply means that the phase clock, spectral phase, has rolled out and there is a linear variation in the spectral phase across different frequencies, underscoring the word linear. We also learnt about using the Jacobian, which has a minus 1 over lambda square factor, coming into play when we want to make a transformation from the frequency to the wavelength variable. We often measure spectra as a function of wavelength and not frequency, more often than not, right? So this is again something we did for a suitable bookkeeping. And now we can essentially consider an example where we take a Gaussian spectrum, that is the spectral intensity, which is this black line on the left panel, versus frequency with a phase that is linearly varying across frequencies, here shown in units of 1 over a femtosecond or femtosecond inverse, as sometimes we may like to call it. The same pulse with its spectral intensity and wavelength plotted appear to be so. The envelope is skewed, it's a skewed Gaussian, and the spectral phase need not actually remain linear in the wavelength domain because of the 1 over lambda square Jacobian factor. So to figure out the rest, although we may measure a pulse in its entirety, recall that we emphasize the fact that a complete description of pulse is not merely its envelope, plotted against a spectral variable, which is either frequency, wavelength, or wave number, we also ought to plot or have the knowledge of the spectral phase as a function of the same frequency variable. In practice, this means that a fingerprint of the or a or a portrait of the pulse must contain two curves, one reference to each vertical axis to the spectral intensity and spectral phase respectively, and you choose to represent it any which way using a solid line for the intensity envelope or field envelope. Very often what we measure is often intensity or a related quantity, something related to the irradiance. So sketch that envelope and sketch the phase function as a function of wavelength over here, say in a dotted line or another color or whatever style of plotting we choose. Convert bandwidths and frequency quantities from frequencies to wave numbers to wavelengths and so on and so forth. And your toolbox for dealing with pulses in the time and spectral domains are ready. Right? So this is where we stood so far, and we have come across quite a long way because we can now formally, mathematically, and physically describe all optical pulses completely without any knowledge or concept or nuance missing. The rest is about interpreting the various details. Okay. The first of which is the concept of instantaneous frequency. We dwelt upon this quite a while in the previous lecture. The instantaneous frequency, instantaneous angular or instantaneous cyclical or instantaneous frequency as we like to call them, is defined the following way. The instantaneous frequency is actually just the first derivative with respect to time of the argument we had to the complex exponential function in our time domain definition of the pulse. The argument was omega naught minus phi of t. So the first derivative in time of these quantities is omega naught minus d phi by dt. Phi here of course is a function of time alone, phi of t. Okay. We also considered various interpretations or routes leading to and motivating this definition. But the point that we really want to bear in mind is this important idea where if I have a time domain description of a pulse, whatever we are plotting across, what we are essentially looking at here is a variation in the frequency of the carrier wave, let's say going all the way from, if this is the zero of time and this is the zero of the vertical scale, and this indeed is a very important concept for us. It is the wavelength instantaneous frequency is redder here and it is bluer here. Maybe in between we should say it is kind of greener. Frequency is locally increasing as a function of the time within the envelope of this pulse. Right? As we have done with the case of angular frequency, we can do the same with respect to the instantaneous frequency, which differ only by a factor of 2 pi, nu instantaneous and omega instantaneous, which is somewhat trivial, I would say. But be aware what you're reading about or writing about in this case. The real deal, however, now begins with carrying all this forward into defining more sophisticated terminology, which we will have to become familiar with and use in the formal description of like pulses, femtosecond pulses, ultra short pulses, attosecond pulses, and so on, where just as we define an instantaneous frequency as the temporal derivative of the temporal phase, that was the instantaneous frequency for us. And I reminded you about this, the fact that omega instantaneous as a function of time was simply the time derivative of this phase factor, which we used in our description of the pulse. Analogous to that, we have a group delay, which is likewise the frequency domain, the frequency derivative of phi of omega, where this is the spectral phase function. This is an analogous quantity, right? But the moot point was this fact that group delay is not the inverse of the instantaneous frequency. That is to say, d, or rather t group of omega, which is d phi by d omega, is not equal to the inverse of d phi by dt. Note here that the phi's that we consider here are in different domains, in fact in conjugate domains. Right? And we looked at the practical detail of phase wrapping and unwrapping in the sense that in a real measurement, phase essentially is going to come out to be something which is modulo 2 pi, right? Ergo, if in the portrait of the laser pulse, which I said should contain two axes, the intensity and the phase axis, a practitioner would often find the fact that the phase function would have these what apparently looks like jumps, okay, like a discontinuous function. It's only owing to the fact that phase being measured always will roll back from, if we use minus pi to pi, then at every pi it rolls back to a minus pi, and or if it's 0 to pi, you go from 2 pi to a 0, and then it jumps back, and so on and so forth. I gave you the example of interference fringes, right? Whereas practically speaking, what we are plotting on the vertical scale is phi of omega. It is a continuous smooth function which can be differentiated many times over. We need that facility of being able to differentiate this function very much. While the main reason for unwrapping may be aesthetics, it's also something we must take care of, if especially when pulses get pretty long and the phase function has a relatively fast variation. Likewise, another matter of detail in this case was appreciating the fact that in a real world measurement, whenever we measure phase, we actually need that to be supported by intensity at that particular range of times or frequencies. Remember that a pulse is a short-lived entity. Its amplitude is non-zero or non-negligible over a very short blip of time. Everywhere else it's as good as being zero because the amplitude is below noise, and any measurement, however sophisticated, done there will lead to considerable noise, uh, playing a role in determining the value for the spectral phase function or the temporal phase function, which essentially noise is inherently high frequency. So we get this, you know, giz glitch or whatever we imagine it to be, which is fairly meaningless. So we can blank all these things recorded to zero, or take an eraser and erase them out legally without compromising on scientific integrity, if I may say such a thing, but keeping the values alive where they actually are of significance. So this is something we are using in making these plots as well, right? Because the frequency and time axis extend infinitely, and we got to be practical here.